Since you have come here, I assume you have already known quite a bit of linear algebra. And as convention used throughout this video, we are going to use Fn to denote the n Fibonacci number, which satisfies the recurrence relation and the initial conditions. First, we are going to transform a vector into another vector using a matrix A. Now, because of these two defining relations for Fibonacci numbers, we have A to be the yellow matrix shown. Give yourself some time to verify that this is the required linear transformation. Now, since we can also do it with lower subscripts, we substitute this back to the original formula, and so ultimately we would have this. What we need to do now is figure out this bit. Luckily, this is actually quite a standard procedure. We first figure out the eigenvalues of the matrix, which helps us find the eigenvectors associated with different eigenvalues. Next, we consider a matrix P that consists of the two different eigenvectors, and then the product of P inverse, A and P would yield a diagonal matrix. The powers of diagonal matrices are much more manageable. Finally, a to the power n can be obtained by multiplying the nth power of diagonal matrix by P to the left and P inverse to the right. We first figure out the eigenvalues. Starting with the characteristic equation, we solve for it. We then call the two roots of the equation to be alpha and beta to save space. The second step now is to find the eigenvectors. We start off with the defining equation for eigenvectors. Usually, we would write an augmented matrix ready for Gaussian elimination. However, in this 2x2 case, it will be trivial to do the elimination, as this only means covering up one of the equations. If you don't believe me, try doing the Gaussian elimination by multiplying the first row by lambda, then adding the second row. Then simply note that the value of lambda should satisfy this equation, as discussed a minute ago. If we then write the vector x as shown, then from this equation, we have x1 to be lambda times x2. The most convenient values of x1 and x2 to take is that x2 being 1 and x1 taking one of the two values lambda can take. Hence, the two eigenvectors associated with the different eigenvalues are these two vectors. The third major step is actually to find P inverse. We start with this matrix P, then we use the formula for the inverse matrix for 2x2 matrices, and directly substitute for it, to get the expression for P inverse. Then we only have the last step to consider. Recall the expression of P and its inverse here. Remember that P inverse times A times P is a diagonal matrix with the two eigenvalues as entries. Now apply this final formula and plug in the known matrices. And now what we need to do is some matrix multiplication. Recall why we have to do all these. This is because we can transform the vector with the first two Fibonacci numbers as entries to another vector with consecutive Fibonacci numbers as entries using a power of a matrix. Unfortunately, the power is n minus 2, so what we can do is go back with the formula for power n and replace all the n with n minus 2. Now substitute this power of matrix back to the original relation, and since the first two Fibonacci numbers are both 1, we get this. By simply comparing the first entry of the vector on both sides, we can finally get an explicit general term of Fibonacci numbers. To simplify this, we simply group up the terms and find out this kinda simplified expression. This can be further simplified though. Notice that right from the beginning of finding the power of the matrix, alpha and beta denote the roots of the quadratic characteristic equation, and here the two roots add up to 1. Going back, with the new relation between alpha and beta, we can further simplify to this, which is the Binet formula. So here is how we can use linear algebra to derive the Binet formula. If you enjoyed this video, leave it a like and subscribe with notifications on. And don't forget to check out the previous video if you haven't already. Bye!